Hello, welcome back to our tutorial video series on the ARP 2600. And this time we're exploring the VCO2 in greater detail. So without further ado, let's get straight into it. Where we left the story was with a very simple tone coming out of VCO1 and not much more happening. But we had just introduced VCO2 into the equation by having a look at it in LFO mode. So that's VCO2 modulating the pitch of the VCO1 via its normal connection here. Let's turn VCO1 off for a moment completely, take it out of the equation. Didn't need to do that, I'll turn that back up. So now we've got no tone. And let's turn VCO2 up instead. So quick recap, VCO2 is now outputting its signal into the filter is outputting its signal into the amplifier, and the amplifier is sending its signal into the mixer. Okay, so what is that? Well, that sounds mysteriously familiar. Go back to 1 for a moment and play this note here. It's exactly the same. It's a square wave, just an octave apart. Why is it an octave apart? Because I forgot to turn control voltage up, keyboard control voltage, so it was playing the default pitch instead of the note that I was asking it to play. Now when I toggle between these two VCOs, we get exactly the same tone. So by default, VCO2 generates a square wave. Well, you can nearly tell that from the VCF legend. Here is the normaled input, and here you can see it's actually a pulse wave image, because by default VCO2 generates a square wave, but a square wave can also be described as a pulse wave at 50%. So its duty cycle is exactly 50% of the time at maximum and 50% of the time at minimum. But we can turn it into something that isn't a square wave by moving the pulse width slider. Now, if you saw my tutorial series on the Moog modular, you may recall that the pulse width options in the modular go from 0 to 50%. And I said in that video that everything above 50% is a mirror image of everything below. So the tone up here, you have a look at that image on span. If you screenshotted those two things, they would be identical. So pulse width allows you to go past 50%, but just bear in mind that this is a mirror reflection image. Everything above is the same as the tone below. That sound, that oscillator, the pulse width oscillator, is exactly the same as this output here. This is the pulse output. If I plug that into there, you get no difference whatsoever. It's exactly the same. Get rid of that. Now then, we can also see that the VCO2 is capable of generating an inverse saw, just like VCO1. But VCO1 can't make a sine wave. Look at that. Look at the beauty and simplicity of the sine wave. And VCO1 also can't generate triangle waves. So we have more flexibility in the tones that we can generate with VCO2. We also have VCO1's square wave output normaled into this slider here, So this will be an on-off kind of ambulance sort of effect. It's going to be horrible at the moment because we're in audio frequency range. There's your on-off, and we can control the speed of the on-off with this. Now, we've not got there yet, but the ability to generate on-off signals like that is really useful. You know, there's any number of effects that will be able to take advantage of this kind of thing. Turn that back down. And then finally, we have a pulse width modulation slider. So this is the first time we've come across a normaled input that isn't frequency modulation. This one here is pulse width modulation. So let's just take a moment to take stock and figure out what that means. This oscillator is generating a tone. It's a square wave, but it doesn't have to be a square wave. Let's make it pure. We just reverted back to 50% to make it a pure square wave. But if we send a signal into this jack here, we can affect the pulse width. So let's do that. Let's take our envelope output, plug it into here, turn the slider up. There you go. All the different stages of the envelope. Let's have a little bit more attack. And a bit more release. Okay, so that's the envelope having an effect on the width of the pulse from this jack here. By default, that pulse width is controlled by the noise generator. So let's have a look at the noise generator. It's not a big module, so we can cover it now. Here it is. At the moment, it's set to maximum, which means that it is generating noise all the time. Again, something really important to bear in mind. Just because you can't hear it and it's not connected anywhere, that noise generator is generating, as it happens, pink noise all the time. So pink noise means it's had some of its high frequencies filtered away. And as we increase this slider, get to the stage where nothing is filtered away and it's now generating all frequencies equally at all times. So that thing is just throwing control voltage data out 100% of the time, but it's not having any effect. Well, if we turn this slider up and we don't have anything plugged into this jack, it is, because the noise generator is normaled into this connection, which means it's internally connected until overridden, and so we're going to hear noise. There it is. And you can see the span is just a big massive green. So just to recap what that's doing, that's having a random effect on the width of the pulse that's being generated by VCO2. If we want to hear what noise really sounds like, we can turn the VCO down and turn the noise generator up. That's noise. There's no tone there. And then you can hear as we move from white to pink, the high frequencies being cut away. That's probably about as much as we want to chew in one sitting. So we've dealt with VCO2 and we've had an introduction to the noise generator. In a kind of roundabout way, we're using the noise generator as a modulation source to something else. But that's great. That's what the noise generator is used for more often than not anyway. So next time we'll bring VCO3 into the equation and have a look at some of its idiosyncrasies, and then we'll be fully armoured from the oscillator perspective and ready to start investigating some of the other modules. Thanks very much for watching. I'll see you next time.